Hi, Rich Neapolitan. In the last talk, I talked about representing causation with Bayesian networks. In this talk, I will talk about learning Bayesian networks, again within the context of causality, so I'm going to be talking about learning causal influences by representing them as Bayesian networks. Again, like I said, I will discuss learning Bayesian networks in the context of causation, learning causation. And I ended the last lecture with this assumption. I want to repeat it. The causal faithfulness assumption means that we assume this probability distribution satisfies the Markov condition, but we assume more than that. We assume that every conditional independency in the observed distribution is entailed by the Markov condition. In other words, the probability distribution and G are a perfect map of each other. That's the causal faithfulness assumption. And it's the ideal situation, in which case you can learn G from P, as we shall see. If that's true, you can learn G from P. And it follows, we assume we have a large amount of data on the variables of interest, and we learn the conditional independencies from these data. For example, let's say we have these data on X and Y. Well, this would tell us probably y1 equals given x equals x1 equals probably y1 given x equals x2, right? Because when x is x1, the probability of y1 is 1/2. When x equals x2, the probability of y1 is 1/2. So these data tell us that x and y are independent. And that's what we mean by learning independencies from the probability distribution. If these were all 1s and these were all 2s, we would learn that x and y are dependent. So we take the data and we learn the independencies and the dependencies and the conditional independencies and the conditional dependencies. And this is described not in contemporary artificial intelligence, but discussed in my book, Learning Bayesian Networks, a 2003 book, and Spiritus and Gleemore's book, Causation, Prediction, and Search. The most recent edition is the year 2000. All right, so we're going to assume we know the conditional independencies. In this first example, we only have two variables, and we know they're independent. What can we learn? Well, we cannot have the causal DAG in A or B, because the Markov condition does not entail that x and y are independent. Remember, in a causal faithfulness assumption, we have to have a perfect map of the probability distribution. This does not say x and y are independent, and they are independent. So we can't have either of these DAGs if we make the causal faithfulness assumption. So we must have the causal DAG in C, namely, neither one causes the other. Now this is a pretty simple example, but it's our first example, and if they're independent, this is what you intuitively think, neither one causes the other. All right, now let's complicate things a little bit. Suppose V equals x and y in our set of conditional independencies is the empty set, meaning they are dependent, then we can't have the causal DAG in A, because that DAG says they're independent. All right, so the Markov condition is violated if they're dependent. Again, the independencies and the dependencies have to be a perfect map of each other, and this says they're independent when they're not. So we must have the causal DAG in B or in C. So if we only have two variables, and even if we make the causal faithfulness assumption, we find they're dependent, we don't know which one caused the other. And that is also reasonable. How could you actually know which direction this arrow went? They both say dependencies. Suppose we have three variables, x, y, and z, and our set of conditional independencies is that they are independent. There can be no edge between x and y owing to the reason example 1. All right, x and y are independent, so there can't be an edge between them, because that would say that they're dependent. There must be an edge between x and z, owing to the example in x and 2. X and z are not independent, and no variables render them independent, so there has to be an edge between them. Similarly, there has to be an edge between z and y, so the links have to be like this. If we have these three variables and the only thing we know is x and y are independent, then we know x and z are dependent, z and y are dependent, but x and y are not dependent, so there's no edge. We cannot have the causal DAG in B or C or D, any of these three. The reason is that this is the first tricky thing, actually. These DAGs say that X and Y are independent given Z. Y is independent of its non-descendant X, conditional on its parent Z. X is independent of its non-descendant Y, conditional on its parent Z. Same thing here. X is independent of its non-descendant Y, conditional on its parent Z. So all three of these DAGs say that X and Y are independent given Z, but that is not one of our conditional independencies up here. So, I'm just staying here. Furthermore, the independency which is present is not here. None of these three DAGs say that X and Y are independent. So we must have the causal DAG in E. This DAG says exactly this. X and Y are independent because X is independent of its non-descendant Y, conditional on its parents, which are the empty sets, so it means X and Y are independent. X and Z are not independent. It doesn't say it, and Z and Y are not independent. So, if we observe these three variables, and X and Y are independent, we can finally conclude something here. We can conclude some actual causation, that X and Y both cause Z. Now note that this is the first time in this talk we're actually able to conclude some causal relationships. If we make the causal faithfulness assumption, we observe this, we can conclude these two causes for certain. Suppose we have these same three variables, and instead of noting that X and Y are independent, we notice they're independent conditional on Z. Then as before, the only edges must be between X and Z and between Y and Z. So we must have the links in A. We can't have the causal DAG in B. So this is the opposite of the last example, because the Markov condition says that X and Y are independent, and it's not true. Furthermore, the Markov condition does not say that X and Y are independent given Z. Actually, because of discounting, they're dependent given Z. So we must have one of these three causal DAGs. Notice we didn't learn as much as we learned the previous example. In the last example, we learned a specific causal DAG. Now we know it's one of these three. Either X causes Z, causes Y causes Z, causes X, or they have a common cause Z, but we don't know which one. Well, let's give a little theorem here that should be intuitively somewhat clear now. If the faithfulness assumption is satisfied, then there has to be an edge between X and Y if and only if they're not conditionally independent given any other set of variables. In other words, when you look at the independencies, if no set of variables renders X and Y independent, there's got to be an edge between them. All right, with that theorem, we can build these graphs a little bit easier. Suppose we have four variables now, and we have X and Y independent, and W is independent of both X and Y conditional on Z. And these are all the conditional independencies. Do that theorem, the links must be those in A. X and Z are not independent given any other variables, so there has to be an edge between X and Z. Y and Z are not independent globally or given any other variables, and same for Z and W. X and Y are independent, so there's no edge between them. W's independent of X, conditional on Z, so there's no edge here. Same thing for W and Y. So these are the edges. We learn the edges first. Then we start directing them. We have to have these edges going in this direction because X and Y are independent. If we have them going like this, it doesn't say they're independent. It says they're independent conditional on Z. Same if they go this way, same if they go from Z to X and Z to Y. So these edges have to go here, and once we direct those edges in that direction, this edge has to go this way. Because if the edge between Z and W goes in this direction, it says W and X are independent. But that's not true. W and X are independent conditional on Z, which is what this direction says. So in this four variable example, we're able to learn three causal influences. Not only that X and Y cause Z, but that Z causes W. All under the causal faithfulness assumption. As I mentioned before, the causal faithfulness assumption assumes no hidden common causes, and in most domains, it doesn't seem we can really make that assumption. We don't know enough about reality to know that there isn't some hidden common cause out there, and we just don't know what it is. All right, like I said, it seems the main exception to the Markov assumption, therefore the faithfulness assumption, is the presence of hidden common causes. In most domains, it does not seem reasonable to assume this. But it turns out we can still learn some causal influences if we relax this assumption. And I call this the causal embedded faithfulness assumption. If we assume the observed distribution is embedded faithfully in a causal DAG containing the variables, so we are making the causal embedded faithfulness assumption. And suppose again we have a probability distribution P of some variables, and V is a subset of W. W is a larger set that we're not necessarily observing, includes hidden variables, and G is a DAG whose set of nodes is W. Then P is embedded faithfully in W if all and only the conditional dependencies in P are entailed by the Markov condition applied to W and restricted to the nodes in V. Now this is a mouthful. And anybody who has figured out what this means by this particular explanation is a much smarter person than me. All right? So I'm putting this down here, but it takes some thought to understand this. It's described in the text, but I'm going to say this more intuitively in what follows next. Basically, when we make the causal embedded faithfulness assumption, we assume there's a causal DAG with which the observed distribution is faithful, but the DAG might contain hidden variables. And you'll see this hopefully now a little bit better when I give some examples, that we're assuming that there is faithfulness going on, but it's not with the DAG variables we're observing, but it's with one that contains hidden variables. And again, I don't think this is possible to get an intuition for until I start showing the examples. So let's show some examples of learning causal influences under the causal embedded faithfulness assumption. Suppose we have these, and this is our first example, and actually our second example before. We have three variables and our set of conditional dependencies that x and y are independent. Before, we learned A. The probability distribution is embedded faithfully in the DAG in A, and we concluded these causes. But see, now we're allowing for hidden variables. And if there's a hidden variable that causes x and z, and a hidden variable that causes z and y, then amongst these variables we have the same situation. X and z are not independent. If we assume faithfulness for this bigger graph, x and z are not independent because of dependency through h1. Y and z are not independent. All right, and x and y are independent because this is a little bit trickier because h1 and h2 are independent. Their children are also independent globally. It's not hard to show that. It's actually a property of something called deseparation, which I have not gotten into, but see it intuitively. If these two are independent, which they are, then these two must also be independent. So amongst my observed distributions, x, y, and z, all I will observe is this independency. But yet there is no causal relationship between these two. So the causal relationship among the observed variables may be this. And the only reason I observe this dependency and this one is because of these hidden causes. So I really can't conclude x causes z and y causes z once I allow that there could be hidden variables. And this was an accomplishment I bragged about before, and now I'm saying if I relax things so I make more realistic assumptions, I can't do anything. However, this is what is really important here, is that if we have four variables, remember I told you if you have four variables, that's when you can learn something. This is an example we had before. X and y are independent, and W is independent of x and y conditional on z. This is the DAG we learned before, and we assumed all three of these causal influences are present. But P is also embedded faithfully in this tag. For the same reason, this edge could be a hidden cause. This edge could be a hidden cause. So I can't learn these two causal influences. And this edge can go in this direction, and we still have the same thing, that W is independent of its non-descendants, namely X and Y, conditional on its parent Z. So exactly the independencies that these four independencies are the ones in this DAG. So this DAG is okay. But P is not embedded faithfully in this DAG. I can't make this a hidden variable. Because if I make this a hidden variable, I've got these two, it's called a head-to-head meeting. These two are independent, which means W is independent of H, which means W is independent of X. And that's not true. W is not independent of X. W is independent of X conditional on Z. So this, once I make this a hidden variable, regardless of whether I've got this situation or this situation for this edge, this could be this one, I've got the wrong conditional independencies between W and X. So I can't make this a hidden variable, no matter what. I've got to keep this edge going in this direction, and we conclude that Z causes W. So here is the most important result of all this. If you have four variables, even if you assume hidden causes could be present, you can, if you see these conditional independencies, conclude that Z causes W. Now what's important about this also is that if you have more and more variables down here, once you start directing this edge this way, there's another variable here and another variable here, we can start directing all those edges. So, as I said, we can learn causes from data on four variables. All right, let's give this some meaning here. It's often argued about, whether smoking really causes lung cancer or not. And oddly enough, I made this example up, and later I saw some actual data which is very similar to this example. Suppose these are our four variables, that the parent smoking history and an individual's alcohol consumption are independent. And once you smoke, lung cancer is independent of your parent's smoking history and your alcohol consumption. And those are the only independencies. Then we can learn this DAG. All right? In other words, your parent's smoking history and whether you smoke. Oh, let me say what these graphs edge. The one-headed arrow means R causes S, or they have a hidden common cause. This is the notation I use in my texts. All right? So this means that R, it's just like a previous example, and now I'm using different notation. So it could be that the parent's smoking history caused your smoking behavior, or they could have a hidden common cause. All right, maybe a genetic defect caused both of you to smoke. It could be that your alcohol consumption had a causal effect on your smoking. I know people that when they drink, they smoke more. I don't know if drinking ever causes them to actually smoke to begin with. Or there could be a hidden variable, again a genetic defect which makes you drink and makes you smoke. But according, the two-headed arrow means S definitely causes L. So if you have these data, you could conclude for certain that smoking causes lung cancer. Again, I don't quite mean for certain. It's only as much as you can believe that these independencies are true, and that depends upon the amount of data you've got. What I mean is that there's no other explanation for these data other than smoking causing lung cancer. Here's an actual example done by the professors at Carnegie Mellon, Gleamore, who wrote the book I talked about earlier, one of the three authors of Causal Prediction and Search. And they looked at a bunch of variables, a bunch of data, which had to do with the effect of the variables that affect student retention. By student retention, graduation rate, I mean the fraction of students who graduate from an institution. It's a goal of every institution to have this number be high. You want the students you bring in to graduate. And they looked at a number of variables. These are the ones they eventually narrowed down to. They looked at data on hundreds of institutions. And these are the variables they thought were important. The fraction of students who are not offered admission, the test score of the incoming students, their SAT scores. Assuming that students with better scores should probably be more likely to graduate. The number in the top 10%, assuming better students more likely to graduate. fraction of students who accept the offer, the average amount of money you spend on the students. If you spend more, will you retain more once they're there? Student-faculty ratio. If you have less students per faculty member, the students get better attention. Are they more likely to graduate? Average faculty salary. It's certainly something the professors, they were professors, they did the study, they're hoping this would have a causal influence, right? But let's look at what they learned. This alpha is discussed in the text, all right? I'm not going to go into it, but it has to do with the level at which you reject a conditional dependency. Again, like I say, we don't learn these things for certain. We reject them or accept them at some statistical level. And so I'm showing this result for various values of alpha, and you get different edges. And as alpha becomes smaller, you get less edges, as you can see. I'm not going into that right now. What I want to show right now is there's only one variable, regardless of where we put alpha, small or big, that has a causal effect on graduation rate. This is what they learned. It's test score. Now this is an interesting result, that according to this result, the only thing that matters as far as graduation rate is the SAT scores the individuals coming in. Good out, essentially. This kind of goes against what administrators hope. They always hope there's something they can do, like spend money here and there, and that'll have an effect, but that's not what this result shows. In fact, after this, Carnegie Mellon based more of its financial aid on merit rather than on need, and they did increase their graduation rate. All right, here's a last example, which is really an interesting example, done actually by myself and a psychologist colleague of mine. And we were looking at a large amount of data on the military and trying to determine which variables had an effect on racial harassment. We narrowed it down to these 5 variables being the interesting one. And the one we're interested in is whether which variable had an effect on harassment. Does race have an effect? Does the years in the service have an effect? This is the incident variable. This is the variable we're interested in. Was there a racial incident? Was the incident reported to the military, and did the hold the military responsible for the incident? We want to see what variables had a causal effect on incident. And again, no matter how we set alpha, we always learned only this causal DAG, which was that response had a causal effect on race. What does that mean? Whether the respondent held the military responsible for the incident could causally affect their race. Which means I could go into the military, have a racial incident, hold the military responsible for it, and come out a different race. This makes no sense, right, in the domain, and it shows the importance of also using domain knowledge in the application. We can't conclude from this that this causal relationship holds because it goes against everything we know to be true. So what went wrong here? I looked at these results quite a while to see what could have gone wrong. And I noticed that the causal influence of response on race would not be learned if there's a direct cause influence of race on incident, which is what we expected to begin with. We thought that our suspicion was that some races are more likely to have racial incidents. And if there was an edge here, I won't go into the mathematics of it, but I didn't notice if there's an edge here, this would not have been concluded. All right, if you go through the algorithm. It seems suspicious that race does not have a causal influence on incident, because that's what we were suspicious of to begin with, that it does. And here is something I realize. These are probabilistic relationships among responses. They are not necessarily probabilistic relationships amongst the actual events. That's a problem with survey data. It doesn't say what actually happened. It said what the patient or what the individual is responding happened. I note here a problem with using survey responses to represent occurrences in nature is that the subjects may not respond accurately. Here's what I realized, that this might actually be what's going on, that race actually has a causal influence on incident, which has a causal influence on whether you say there's an incident, right? Because if you have an incident, you're more likely to say you have an incident. But it also has a causal effect on whether you say you have an incident, because races that are more likely to have incidences might be more likely to keep them quiet because they don't want to suffer the ramifications of reporting. So what we're really interested in is this variable, but this is the survey response. This is the one in our data. We don't see this variable. We see this one and this one. And it could be that races which experience higher rates of harassment are less likely to report racial harassment. So the causal effect on race on says incidence through incident is negated by this direct edge. This is a case of where the embedded faithfulness assumption is violated, similar to the finasteride example. There's a conditional independency which the DAG does not say. Says this incidence is independent of race because the dependency through here is negated by the dependency through here, but you can't read that independency off the DAG. And there is evidence that minority members are less likely to report discrimination publicly, and so they might also be less likely to report it in a survey. And we actually published these results because they were good results to show the caution you need to have when you use these data. And it goes back actually to this whole idea when I started these talks 10-some talks ago with I don't think I mentioned Jack Good's quote. Jack Good is the Bayesian who I said helped decode Enigma. Enigma was the Germans' code for passing messages in World War II using Bayesian methods. And Jack Good said that anybody who's ever analyzed a lot of data knows that it's not simply a matter of doing cookbook and getting a result. That you have to carefully look at the data. Same thing here. If we just do a cookbook and use these Bayesian network learning techniques, we would conclude that reporting an incident has a causal effect on race, that our study substantiates that. And it's silly to report that. When we look at things more carefully, we have an explanation for it, and we can report that. So just like any use of statistics, use of these methods for learning Bayesian networks has to be done carefully and thoughtfully, not in a cookbook fashion. And this actually ends my talk.